Okay, so this is lecture number 2, and here we're going to talk about how to use Taylor series and Chebyshev economizations. Um, how many of you have responded to an email asking you for your bank account numbers? Oh yeah? Sorry? Oh, do you? You're one of those. Okay, but I mean, how many of you here have done something really stupid like open malware or something? Sorry, that's probably a little too much, but Chebyshev economizations are a method of taking a more complicated polynomial and reducing it to a simpler polynomial. And you're probably saying, Tom, come on, man. There's got to be another use for it. Yeah, there's lots of uses for Chebyshev polynomials, but this one, the economization, I'll do a demonstration in a minute. We'll start with a fifth order polynomial and reduce it to a third order polynomial. There's no such thing as something for nothing. If I take a fifth order polynomial and reduce it to a third order polynomial, am I going to get the same accuracy? No. But I will get a simpler function. And in this day and time, that may not mean a whole lot to you, but it may mean something to someone else. So it's worth at least talking about it. Then we'll look at the derivation of the error function. What's the easiest way to derive the error function? Well, the easiest way is to take a Taylor series for exp and then simply integrate it. Okay, and that's exactly what we'll do. We'll show how to take the Taylor series that we derive for exp, substitute it in the definition of ERF, and then get this thing. And I know this is really ugly, but it's actually really simple. So that one's going to be hopefully fun for everybody. The error function, what does it look like with your finger? Error function starts at 0, it's 0. What's its maximum value? 1. So somehow this thing has been scaled to where it's 0 to 1. Is there a variety of different things you could use here? Yes. The error function obviously came from some sort of a statistical distribution, hence its name, the error function. But there could be any one of a number of variants. David, do you want to comment? I know you looked at a number of different types of arguments, but yours had an exponential raised to an exponential, right? Yeah, with another time argument inside of it. Okay, as opposed to this being symmetrical on a Cartesian scale. Okay, I see your point. Good point. Whether it's practical or not depends on the problem, though. And okay, so now we'll talk a little bit about how the derivation of these relationships is given in full detail in Hornbeck. So I didn't put that on here, but the entirety of these derivations is given in Hornbeck. This I of x is going to be the integral over the distance x0 to xn. It could be a partition, it could be a complete distance. And in this case, it's delta x over 2, again, multiplied by f of x0 plus f of n of x, which is one of the terms of a trapezoid. And then all of these others, it no longer looks like a trapezoid because they factored those terms out into this summation. The error term, or the residual term, whatever you want to call it, no, the remainder term, pardon me, is delta x squared over 12, and it's multiplied by the derivative of f of x evaluated x of n minus the derivative of f of x evaluated x0. So that would be this is the part that would be your add-on term to try to correct the trapezoidal rule. And then Simpson's rule, it also has a correction. Simpson's rule has a sequence that's both odd and even. It references the initial and the final value, and then there's a summation for the odd terms in x of I, and then there's a summation of the even terms, f of x of I, and then at the end, there's delta x to the fourth divided by 180 multiplied by this difference, again, xn minus x0, raised to the fourth derivative of this, evaluated at the average value of x. Again, I don't want to make too big a deal out of this because the derivation of both of these is in Hornbeck. But the nice thing about the algebra going in the Hornbeck text is that you do figure out how to derive these remainder terms, which is kind of clever. Obviously, you have to make some decision about how you're going to truncate these series whenever you're deriving them. And so, you may say that because there's a first derivative here, that the trapezoidal rule with correction is second order correct. And because there's a fourth derivative here, you may say that Simpson's rule with correction is fourth order correct. If you wanted to assign some sort of a jargon to it, you could do that. Next is, the definition of a Gaussian quadrature and then Laguerre quadrature. Gaussian quadrature is an integral from x0 to xn, just like we saw before. It's the function f of x being integrated. It's approximately, and approximately because it is a numeric calculation, xn minus x0 over 2, and then the summation from I equals 1 to n, and you specify n. You personally will choose n. The weights, which is the sampling weights, multiplied by the function evaluations at zi, and zi is a location, which is given by this formula. So that's how Gaussian quadrature works. The weights x of I and w of I are given in many different kinds of numerical analysis text. There are some tables for wi and x of I in Abramowitz and Stegen, which is the main reference for this course. There's also, there are books entirely devoted to Gaussian quadrature and Laguerre quadrature. Start looking at Laguerre quadrature. The difference here is, yes, it starts at 0, and yes, it ends in infinity, and yes, it has an e to the minus x dampening function multiplied by f of x, which, what does that look like? What does it smell like? The Laplace transform. Okay, so making a slight variable change in Laguerre integral gives you the Laplace transform. So this will be useful for us if we want to try to use this to calculate the Laplace transform of an analytic function. There are methods in the literature of using Laguerre quadrature for an inversion of Laplace transforms. I, like you, now that I've said that, you probably think, well, okay, I bet I can rearrange this into giving me a formula, because the more terms I specify, the more n values I specify, the higher order the accuracy of Laguerre or Gaussian quadrature. By the same token, if I'm going to reverse solve these and I'm going to try to use it as an inversion formula for Laguerre quadrature for the Laplace transform, your brain might be saying, well, the more terms I take, the more accurate it'll get. It doesn't work that way for Laguerre quadrature. It has when we talked about the Laplace transform, I'll show you how to derive a Laguerre quadrature formula for the inversion Laplace transforms. It is absolutely exact for what kind of function, class? Just like Gaussian quadrature is exact for what kind of function? For polynomials. Okay. If you select the order of the polynomial that you're going to use the weights and abscissas for that is greater than or equal to the order of the polynomial of the curve you're trying to work on, you get an exact answer. Duh. I mean, that's what it was derived for. The same thing's going to be true with Laguerre quadrature. But do you have polynomials? Is everything polynomial? No, of course not. So it's not going to work out very well. It's a nice story. Unfortunately, it's not going to work out. Okay, how many of you have derived from scratch the least squares equations? Uh-oh, I see a problem for the exam or for the assignment. All right, so another nice thing about Hornbeck is he shows how to derive the so-called normal equations for least squares. Now, in this sense, we're talking about least squares being a polynomial. What can you tell me about this system of equations? Okay, very good. Is it solvable? Does it have a solution? When you apply least squares to a polynomial, this is the result. So does this solution exist? Yes. It is a unique solution. Okay. This is not what solver uses. Okay. There's only one pass. All you have to do is solve this matrices, and you get the answer. I didn't say the answer's right. I didn't say that fitting a polynomial to a logarithm is going to give you coefficients a0, a1, a2, whatever, that exactly match that behavior. Obviously, it's not going to work because the universe is not polynomial. But this has a singular answer. This has all sorts of different names. The easiest way I think about this, and it's not meant to sound linear like a straight line, but here you're using a polynomial, so this is going to have a result. May not be right, but it's going to have a result. This is what you get when you use trend line in Excel. Okay. What happens if the problem is not constructed with a polynomial, but it's in let's say is constructed with some other kind of equation? You have to use a completely different kind of solution approach, hence solver. When you look at the references in Microsoft Excel for solver, there are something called the DUD algorithm. You know what DUD is? Doesn't use derivatives. These are all actually derivatives, but because it was a polynomial, all the terms fell out as summations. And this is a great opportunity for you to understand what normal equations look like. I mean, this guy was ahead of his time because he showed how to do this really straightforward, clever, simple. So if least squares for polynomial is, this big, the rest of the room, the rest of the College Station, the rest of Texas is where nonlinear problems arise. And by that I mean things that cannot be broken down into a simple exact answer. I'm probably not getting the words right for people who do numerical analysis, but this is where you're going to have to use Levenberg-Marquardt method. You're going to have to use what's in solver. Now, Levenberg-Marquardt method requires derivatives. How do you calculate the derivative of the objective function with respect to the parameter? How many of you heard those words? It's just wah, 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 wah. Okay, because when you do the derivation of the normal equations in the Hornbeck text, the derivative of the parameter, the derivative of the coefficients, if you want to call it that, they fall right out. It's very obvious. Okay. But in another case, how are you going to estimate the derivative when the problem is not linear? When the problem is not polynomial, sorry. What's going to happen? Sorry? It's not just errors. This is where all sorts of different algorithms like steepest ascent, steepest descent, those kind of things come in. Successive substitution doesn't use derivatives. That's where you just keep substituting the previous solution in. How would you look for a solution if you were an algorithm? There's only one solution for this set of equations. But if you were looking, let's say you were going to make your own algorithm to try to solve a 3-parameter problem, how would you do it? Okay, let's make it easy. Let's do 2 dimensions. How would you do that? Right, but how would you select A and B? Sorry? Okay, you have a surface. That's correct. And you're going to look for the minimum in that surface. Or it could be the maximum, but usually we're looking for the minimum. How many of you had a dog when you were a kid? Anybody here? Yeah? Did your dog like to chase the ball? Yeah. So we had a backyard that was sort of a rectangle like this, and this dog would chase the ball until she was exhausted. And finally I got tired of it, and I would just pretend to throw the ball, put it in my pocket, and go back in the house. What would the dog do? There's a lesson here. How? What's the first thing she would do? She would trace the fence. you're right. The first thing she'd do is go look where she started, and then she would trace the perimeter of the fence, and then she would start cutting across. So my dog is actually a nonlinear optimization algorithm, I guess. Okay. So that might be one way of thinking about this. But for this course, this is simply, we're going to derive it this way. Now, there is a nonlinear problem that they have in this particular set, and they show it's a very simple nonlinear problem, so it can be broken into pieces. But he does show how to do that for this case. So this is a great, thank you for your honesty, because if you've never done this, this is a nice exercise. Okay. Now let's talk about the definition of the ERF and then its series expansion. So as I mentioned before, we're going to take the exponential, we're going to expand it with a Taylor series expansion, then we substitute it, the infinite series form, or term by term if you wish. We substitute it into the definition of the ERF. We have that 2 divided by square root of pi out here. We have our integral. Of course, this summation comes out front. This minus 1 over n factorial comes out front, and we're left with just the integral from 0 to x of t to the 2n dt. And when we integrate that, we have 2n plus 1, and then we have a in the denominator as well because of the integration of that power term. And we have an alternating sign series, which doesn't change. We still have an n factorial, and I guess, to be honest, we should pull that out in front of that, but we end up with ERF is equal to 2 over the square root of pi, which is from here, and then the minus 1 of the n, which is from there, and then the n factorial, which is from there, and then we get 2n plus 1, which comes from the integration of this, and 2n plus 1, which comes from the integration as well. So this is a very straightforward calculation. How accurate is this in your book? What do you think the likelihood is that this is going to be very accurate? What's your brain telling you? Okay, let's take a look. So the error function, and I apologize, I'm like an artist. This was my black and white face, so I didn't have any color here. The error function is this trend that does this. Of course, it intersects at 0, and then it rises up and does this. So a single term expansion is just going to be a straight line. Obviously, it's going to diminish. 2-term expansion here. 3-term expansion there, 6 terms there, 7 terms there, 10 terms there, 11 terms there. So, okay, I realize this is a pretty neat problem, because after about 10 terms, actually maybe even more like 7, this thing has gone to 0.9999999999999, which is more than accurate. But what was it we were talking about before, that not thing? Remember, we talked about what happens. So if I just truncated this at 10 terms and I said if x is greater than 2, then ERF is equal to 1, there would be a not right here, or a bump, and that would not bode well for us differentiating it. And I realize, you have on your calculator, or you have in Excel, or you have anywhere you want this ERF calculation. But when I was your age, and I know you're going, oh God, another story like that. ERF did not exist on a calculator. ERF did not exist in a computer program. So all of us, and of course it was required for the hydraulic fracturing class, which Dr. Holditch taught, all of us had to write a subroutine for ERF. And, people got as clever as they could. Some people wrote, using the Taylor series. Others went back to that Hastings book and got the terms out of there. But you can see what's going to happen if you truncate this thing. You're going to get a knot or a splice, and that could cause problems. Now let's look at what happens when we take the sine series. And we didn't show this, but when you take the series for sine and you integrate it, you're going to get this expression. And when you do that, that's the Taylor series, pardon me. The first term is going to be here, and then the second term is here, third term's here, fourth term's there. I mean, I guess you could say, okay, if I can get a complete half period of this thing, then I can work out the algebra to figure out where I am, and I can flip it. So all I really need to do is get enough accuracy. Maybe the 5-term or the 7-term equation is accurate enough to do this, maybe 9 terms, maybe 11, whatever you might want to use, because then you have the entire 2 pi period. You could use something like that. I also showed the 2-term Chebyshev series. You get a little bit better accuracy with a 2-term Chebyshev series. You get a little bit better accuracy with a 3-term Chebyshev series. You get a little bit better accuracy with a 4-term, with a cubic fit, which is going to have 4 terms as well. Should have said that. But you notice over here, you've lost something. So when we did the Chebyshev and the cubic fit, where we benefited from it away from 0, we lost our origin term. So, and again, my apologies for this being my black and white phase. Perhaps I should insert a color trend on top of this. But this is an example of how to create a calculation for, say, the sine of x using a Taylor series expansion. Okay. The next slide is looking at the Taylor series expansion for EXP. And very quickly, a single term expansion is meaningless. 2-term expansion is here, 3-term here, 4-term here. Did a 4-term Chebyshev, it didn't really help. 5 terms, 6 terms, 7 terms, 8 terms. We're really expending a lot of terms out here, and they're only accurate out to maybe x equals 3 or 4. So, and you can see, okay, so I made the y-axis semi-logarithmic, so it would be linear in terms of this term curve, so we could see it a little better. But getting actually to match, that's going to be a pretty big challenge. You're going to have to use a lot of terms. Next is a discussion about Chebyshev polynomials. You have the Chebyshev polynomials over here. You have their inverse over here. And the way this is going to work is we take our definition. Let's say we have a polynomial. Then we'll insert 1 for the constant term, x for the x term, x squared for the x squared term, x cubed for the x cubed term, truncate if we have higher order terms, and then we'll reinsert the Chebyshev polynomials, work out the algebra, truncate from that. I've got an example of it. And in this example, we're going to do a Chebyshev economization for EXP. We have the Taylor series, 1 plus x squared over 2 factorial, blah, blah, blah. And then we have the exponential in terms of the infinite series. So as I mentioned, the way we're going to do this is we're going to go grab the t0 term is equal to 1, x is equal to t1, x squared is equal to that. So everywhere you see this, so here we have a 1, so that's t0. Here we have an x, so that's t1. Here we have an x squared term, so we factor that out. That's going to be 1/2 t0 plus t2. And then we have an x cubed term, and you can see we just keep carrying on and on. I put an epsilon here to represent that we are going to truncate. So then we work out the algebra to where we're only in terms of t0, t1, t2, t3, t4, t5. And we're going to close our eyes and we're going to say, okay, I'm at a point now where I'm going to neglect the t4 and higher terms. So I'm going to go ahead and I'm going to just say I'm not going to go any higher than t4 or t5. And whenever I substitute in these terms for that, t0 is 1, t1 is x, t2 is 2x squared minus 1, and then t3 is going to be 4x cubed minus 3x. We work out the resulting algebra from that. Apologies for going a little fast here. And this is the final number. So this actually should be 1, this should be 1, this should be 1/2, and this should be what? What is the factorial here that it should be, class? 1/6. Yeah. So, but it's actually 1/5, or a little bit less than that. So you see what happened with the Chebyshev economization is we took a 5th order polynomial and we reduced it to a 3rd order polynomial. And although there's a bunch of decimal points or a bunch of numbers on the other side of the decimal, we did lose some accuracy at the origin, which is probably not what we wanted. And also we've lost a little bit of accuracy along the way as well. But 50, 60 years ago, this would have been more than sufficient for calculations. All right. Next is a discussion about using cubic polynomial in this assignment in Hornbeck. I'm not saying I'm going to give this to you, but I may. So the data are x and y. Here's the pairs here and here. I moved the other side of the table over here. So this is what the data look like. Does anybody not see the sine wave here? Okay. What if that line wasn't there? Would your brain still see the sine wave? Okay. Okay. So how many of you have Dr. Dattagupta as your advisor? Anybody? Yeah. Okay. Nobody else? I thought your advisor was Dr. King. Okay. So they both your advisor? Are you lying now or were you lying then? Okay. Anyway, Dr. Dattagupta wrote a paper back in 1994 on an algorithm that came out of Stanford. Dr. Valco did some work on it as well. So did I. It was a really clever approach of using non-parametric regression. If you send this data to that algorithm, what does it do? It removes the Gaussian noise. And so the outcome of that algorithm is it produces a perfect sine wave. Because the algorithm has, I confess, not my area, some mechanism for inverting the noise back out of it. And the nice thing about non-parametric regression is that you can have any number of parameters or any number of variables you want or any number of independent variables you want. You can compare the cost of cotton candy with the size of shoes with, how much electricity you used last month or last year, whatever it may be. There may or may not be a relation in that, but when you look at something that's a simple 2D relationship like this, it was really clever how it just extracts that back into the original sine wave. Neither here nor there. If you do a quick curve fit with a cubic order equation, this is what I've done here. This was the approach and intent of the Hornbeck example. And I know you're all going, well, just right click and do trend line. Yeah, I got it. But it's a much harder approach, which is to actually solve it. And by going through the definition of least squares, okay, so here's I know you're ready to go, but here's a really good thing. Why would we define our problem in terms of least squares? What does least squares mean? We're minimizing the distance between that line and those points, right? Wrong. We're minimizing the square of the distance. Why do we use a square? It provides an absolute value, okay? Now, when you use Excel, you set up your vector of what you're going to optimize on. Does it have to be squares? No, it does not tell you that. My advice is you always set it up first as squares so that you're at least doing that. But you could set it up as the absolute value of the distance. Why? Because it's not a least squares algorithm. It doesn't use derivative algorithm. Okay? So it would be nice if we could just minimize the distance between these two. G of x is your calculated function, which is a straight line, and then f of x is the data points. It would be nice if we could do that, but we can't. Okay? So the way we're going to do this is we're going to do it in terms of the distance squared. So our area is going to be, our error is going to be the sum of the squared residuals. Okay? The sum of those distances squared. Why? Because for a polynomial g of x, a0 plus a1x plus a2x squared, blah, 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 then we substitute that polynomial into this definition, and we're going to get a very nice result out of that. By doing that, by substituting 7.3 into 7.4, we're going to have that our error looks like this. It's going to be, again, a polynomial. And now we're going to take the derivative of the error function, or of the objective function, that's what it's often called, with respect to each of the coefficients. Now this is probably new to you. You probably haven't thought about this before. But what you're going to do is you're going to minimize the sum of the squared distances, or sum of squared errors. But the way you're going to do that is by setting up a matrix of the error, with the derivative of the error with respect to each of the parameters. And the way we do that is we set them equal to 0, and then that gives us a linear system. How do I know it gives me a linear system? What's the easiest way your brain can process? You know this has to be a linear system. Why? You're working with a polynomial. If you're working with a polynomial, you're performing derivative operations on a polynomial. What's going to happen when you take the derivative that's equal to the highest power of the polynomial? You're going to reduce it to simply that last term. And when you do that, you're going to have a system of equations that will reduce to. So here's term by term. You know, the first equation is going to be the number of terms in number of data points multiplied by a0, the summation of the number of data to the number of data points of the x of I values, and so on. And then on the right hand side is the summation of the y values. And then you're going to have the summation of x of I times a0, so it's not n anymore. And we're going to just continue to build this pattern. So the first one is n, the second one is this term, the next one is that term, and then build ourselves out to here. The next one is a summation of x of I, the next one is summation of x of I squared, x of I cubed, on out x of I times f of x of I. We keep working, keep taking derivatives until finally we end up with the term raised to 2 times L, and then the Lth derivative, which is the highest power, and then f of x, those variables multiplied by that. Can you solve this linear system of equations? Yes. Does it have a unique solution? Yes. It doesn't matter how you solve it. You're going to use Gauss-Jordan elimination, but you can solve this directly. So there is always going to be an answer for this. And again, you see it's saying that they're simultaneous linear. You don't want to call this linear least squares because it confuses people with a straight line, but this is a linear system of equations that is simply solved by reducing this matrix C and solving for the coefficients A, the A coefficients. And so here's the data again, and here's the setup, and then they go ahead and use Gauss-Jordan elimination and solve for these coefficients. I believe that there is a slight error in this calculation. I believe that there is, in the textbook, there's a slight error in here. You may want to check that if this is assigned. Okay. And then the final equation looks like this. This is a cubic fitted to the data. Now, they also have other equations that are fitted to the data. One is a constant and then a multiplier or a slope term, if you want to think about it that way, multiplied by sine pi over 10 to the x. The reason is the relationship here is that this is sine of pi over 10. You can see that where it intersects. And then there's a nonlinear equation. This is a sort of linear equation. There's a nonlinear equation where you actually determine the coefficient of which sine is being evaluated against. And you know, if you do this in Excel, you'll be done in 5 minutes, but of course that's not the goal of the problem. So I hope this made sense to you tonight. Having talked with you, I think we need at least one problem on this. I'll make a decision on how hard or easy to make that. It's going to be a book problem, so it'll definitely have an answer. And please do show all your work. If I ask you to do this, don't just simply say Excel said. I'm going to provide a rubric for all of the problems. You know, there'll be like I do, where, you know, determining the coefficients will be worth 5 points, determining or, you know, doing the derivation is worth 5 points. Let's say each problem's worth 10. You know, if you fail to do one of those things, then the grader will deduct points for that. So you really need to focus on showing all the work that you're asked to do. And that is our last slide. So go ahead. Are you looking to see the steps? I'm looking to see everything. Yeah. But I'm not, you know, I'm not going to grade you, or you don't have to show me Gauss-Jordan elimination, you know, row by row. But I will want to see all the work leading up to that. Once we get there, can you just do like a matrix inversion? But I still want to see the elements of the matrix. I want to see the numbers in something that looks like a matrix. Yes. I need to know that you did it. Once you set up the matrix, then you can solve it. I'm not prescribing how you're going to do this, but I will expect to see evidence of progress through the calculation. The example they give, they show step by step. I would expect something like that. It may not be easy. Look, you guys are grad students. I'm not going to torture and torment you on little things, but if you just say, I did it in Excel, well, you know what? You're going to get to do it again or accept the punishment for not doing it the way you were asked to. But I want to find a new problem or maybe a new methodology. I suspect what I'll do for this problem, and I'm not making an assignment, I'm just making comment. I suspect I'll ask you to reproduce the derivation of the normal equations, which is a great exercise, and then I'll give you a problem to solve with that. And it may be this one, it may not be. This one is the only one that they worked out in excruciating detail, and it is a nice problem, but I mean, something else might be interesting as well. Can you think of a problem that you'd like to solve with this? Why do you have the bucket on your head? Uh-huh. Okay. Well, good. I was planning on meeting every day this week, but I think we can just meet on Wednesday. Are you guys okay with that? Yeah. I might want to meet on Friday, maybe. Is there anything on Friday of this week? Hmm? What? Drinking. I can't help you with that. Is there a football game here this weekend? Well, there it is. Because I'm gone most of next week and the week after with SPE. So, um, no, we can do something else. We can. Oh, when does it end? Let me double check. Uh, I see your point. Um, yeah, let me make sure. But if we meet on Friday, I'll definitely try to be earlier. No problem with that. I was just trying to think. I know that the people who are in here don't want to leave, just like I don't want to leave when there's people in here who shouldn't be in here. But yeah, we'll work something out. And then we'll meet on Monday. And unfortunately, I have to leave 2 days early for the board meeting, so I'll have to leave on Tuesday. But that's neither here nor there. We'll meet on Wednesday night. We'll make a decision on Friday after that. Okay? All right. All I ask is one piece of pizza.